Start with the baseline of what we know today: the 24-hour day, 4 reliable seasons, and the gentle, rhythmic washing of ocean tides. But go back 4.5 billion years, and you wouldn't recognize our planet. Earth was spinning so fast that a single day lasted barely 10 hours. That rapid rotation whipped the atmosphere into a frenzy. Super hurricane-force winds tore across a dark, barren landscape, continuously battering the young crust. It was an entirely hostile environment. Complex biology never could have survived here, because the Earth lacked the one thing it needed to settle down: a stabilizing gravitational partner. The fix came in the form of a Mars-sized protoplanet we call Theia. According to the giant impact hypothesis, gravitational nudges knocked Theia out of a stable orbit and set Earth on a new path. This diagram shows the mechanics of the collision. Instead of a head-on impact, Theia struck Earth with a glancing blow. The heat melted both bodies and drove Theia's heavy iron core deep into the center of our planet, while blasting the lighter outer rock into space. All that vaporized and molten debris trapped in Earth's orbit rapidly clumped together. Within a remarkably short time, it condensed into a glowing molten sphere. Planetary models suggest Theia might have been composed of up to 50% water ice before the crash. That means this collision likely delivered the frozen resources we now find buried in lunar craters today. The impact forged a dual planetary system, locking both bodies into a shared evolutionary orbit. Following its fiery creation, that molten moon sat much closer to Earth than it does now, and it spun rapidly on its own axis. Looking at this cross-section of the Earth-Moon system, you can see how Earth's immense gravity pulled on the newly formed moon. Because the lunar rock was hot and elastic, that gravitational pull stretched it into a slightly oval shape, creating what we call a tidal bulge. As the moon spun rapidly through this distorted shape, the physical rock had to rise and fall. That constant flexing and squishing of the lunar mantle generated immense internal friction and heat. Over millions of years, that friction acted as a massive cosmic brake. It gradually slowed the moon's rotation until its spin perfectly matched the time it took to travel once around the Earth. We call this state synchronous rotation, or tidal locking. Because of it, humanity has only ever looked up to see the exact same hemisphere of our celestial neighbor. But physics dictates that angular momentum must be conserved. This gravitational tug-of-war is a two-way street. Just as Earth pulled on the moon exerts its own gravitational pull on Earth. It grabs onto our liquid oceans, drawing the water upward to create the terrestrial tidal bulges we experience at the shoreline. This diagram shows how the timing works. Because Earth completes a rotation much faster than the moon finishes an orbit, the speed of Earth's spin actually carries its ocean tidal bulge slightly ahead of the moon's position. The moon's gravity continuously pulls backward on that leading pocket of water. This creates a torque, a literal braking force dragging against the Earth's spin. Slowly, over billions of years, that drag stretched our violent 10-hour day into a calm 24 hours. By slowing the planet down, the moon killed the super hurricanes. Its massive bulk also acted as a gravitational anchor, holding Earth's axial tilt steady and preventing extreme, chaotic seasonal swings. Without this constant, draining exchange of momentum, bleeding energy out of the Earth's rotation, our climate would have remained too volatile for complex biological life to ever take hold. This mechanical exchange hasn't stopped. Because the moon is continuously stealing Earth's rotational energy, it is slowly spiraling about 3.8 centimeters further out into space every single year. While we often treat the moon as a static relic, recent findings from the Smithsonian Institution show it is actually far more active than we once believed. The lunar interior is still slowly losing heat from its molten birth. As it cools, the entire planetary body is actually shrinking. Looking at this cross-section of the lunar crust, you can see how global contraction creates intense compressional stress. As the surface shrinks, the brittle crust breaks, pushing sections of rock up and over each other to form thrust faults, lobate scarps, and small maar ridges. These thousands of newly mapped young tectonic features prove the wound is actively modifying its own surface today. The formation of these ridges is not a silent process. These shrinking fault lines serve as the epicenters for violent, shallow moonquakes. Because the lunar crust is completely bone-dry and rigid, the rock doesn't absorb vibrations the way Earth does. Instead, it rings like a massive tuning fork. Quakes reaching 5.5 on the Richter scale can violently vibrate the surface for over 10 uninterrupted minutes. These prolonged seismic vibrations pose a severe threat to the upcoming Artemis program. Tall, top-heavy landing systems and human habitats cannot withstand 10 minutes of intense ground shaking without catastrophic risk. Mission planners must now rely on these newly generated tectonic maps to chart safe zones, ensuring human shelters are built far away from active fault networks. This shifting frontier is the live testing ground where humanity will face its first true challenge in deep space.